Alright gang, here we go. This is for Chem 1, Unit 9, Part 4. We're talking about vaporization, boiling point, so on and so forth. Alright, so vaporization is defined as the general term for the conversion of a liquid to a gas. Okay, so remember, generally when we talk about molecules, or the changing phases, really we have to think about what they look like. So if you have some beaker that's full of some solution, they've got these molecules in there, right? Whatever it is, or these formula units of whatever thing you're talking about, whether it be water, benzene, liquid nitrogen, doesn't really matter. We can kind of think of them as individual point particles. And when they're liquid, right, they're all condensed, they're close together, and because there's intermolecular forces pulling them together. And the stronger those intermolecular forces are, the more they'll be pulled together. All right. Now, if you have a gas, right, and we'll just close this off because it's a gas, these particles are still there, but they're much more spread out. They have a lot more kinetic energy, so there can be a lot more space between them. Okay, and so essentially what needs to happen in order for vaporization to occur is these individual particles have to get enough kinetic energy to break their intermolecular forces. Okay, and once their intermolecular forces are broken, they can spread apart from one another, and then they start acting like a gas. Okay, and so essentially the intermolecular forces are the thing that is holding them together in the liquid state. And this is pretty much true for the transition from solids to liquids as well. We'll talk about that more in a future video, but essentially all these phase changes you can think about in that term, this breaking those intermolecular forces with more and more kinetic energy. All right, now this part here, vaporization is a cooling process. Okay, so I want to focus on this real quick. Remember when we talked about, oh, that was not my best line, but anyway, when we talked about the kinetic energy of molecules, we had like a number of molecules here. Okay, in the left-hand side, really this would be formula units, not molecules, but I keep saying molecules, so we're going to run with it. And then this would be the amount of kinetic energy you have. And remember how we talked about how at any given temperature, our curve, our distribution of kinetic energy would look something like this. So the higher this peak, the more molecules have that kinetic energy. Okay, and then remember we said, well, for, at any given temperature, anything past this dashed line here, okay, any of these molecules would have enough kinetic energy to break free of those intermolecular forces and would be able to vaporize. And depending on the substance, this dashed line would be at different points. Obviously, for something that has really, really small intermolecular forces like hydrogen, this dashed line would be way over here. For something that has a lot of intermolecular forces like water, it's going to be farther to the right. But anyway, so what occurs is at any given temperature, so you're going to have some things entering the vapor phase. That's just what occurs, right? We talked about vapor pressure in the previous video. Okay, and so this kinetic energy is distributed like this, and then the ones over here are the ones that are going to have enough kinetic energy in order to transition into the vapor phase. All right, and then once they leave, so then this is all the molecules that are in your beaker, right? Once these guys leave, the highest energy kinetic, or the highest energy molecules have left your solution. So you can imagine that all of these are now gone, okay? And then so only this is what's left in your beaker. These guys, because they have a lower kinetic energy, their average temperature has gone down. And so therefore it's cooler, right? Okay, so that's essentially what we mean, that vaporization is a cooling process because the highest energy molecules are leaving and leaving behind the low energy molecules. All right, and then, but because we don't do these things usually where heat cannot transfer, that's called adiabatic processes. Okay, but anyway, so because energy can transfer, energy from the outside travels into your beaker, okay, and it will reestablish this curve, and then more of them can evaporate. And essentially that's what happens when you like spill water on a table outside, right? Parts of it, the highest energy molecules will be able to evaporate, okay, and then the ones that are left are technically cooler, but they'll immediately start warming up because the sun is hitting them. All right. So anyway, so vaporization is a cooling process, so that's important, but it can happen in two distinct ways that I want to talk about. We have boiling and evaporation. The nice thing about these is that you should be familiar with both of these already, but we're just going to focus. We're going to try to talk about things in a slightly different way than you're used to. All right, so evaporation, let's do that one first because it's kind of the easiest to understand. All right, so evaporation, right? We've got these molecules, and these molecules are close together because it's a liquid, right? And they're kind of doing them thing. And we've got these molecules that are throughout the solution, right? Not just at the top. But really, we want to focus just at the top because we know that essentially, remember, we just defined what needs to happen is that these guys need to have enough kinetic energy in order to break free of their intermolecular forces. So you can imagine a case where some molecule underneath them has a lot of kinetic energy, will reach up, boom, and run into one of these top molecules, and then this guy would have enough kinetic energy to escape and then become a vapor, right? All right, and so essentially that's what's occurring whenever things evaporate, is that these guys up here are getting hit by molecules underneath them, get enough kinetic energy, and then they bounce off to become a vapor. And that's essentially all that's going on. Now, it's an interesting thing is that it has to happen at the surface only, okay? You can't have evaporation anywhere other than the surface, all right? And because these molecules that are underneath, they can't escape. They'll run into another one if they try to go upwards or to downwards or whatever, left and right, forwards, backwards, okay? So it has to happen at the surface, and it's really all about the kinetic energy, okay, breaking your intermolecular forces, all right? Now, boiling is a totally different matter, all right, ish. All right, it's an interesting matter. All right, so if we have boiling, and you guys have probably made macaroni and cheese or ramen noodles or spaghetti or something like that, so you're used to seeing water boil. All right, and when you see water boil, you see the first signs that your water is boiling. It forms little bubbles, and that those bubbles form next to where your heat source is, and that makes sense because that's where the hot is. So that water is going to get hot first. Now that water is breaking their intermolecular forces so much that they can form bubbles. So we're just going to draw a little bubble in here. Okay, so usually they form sticking to the outside, but we're just going to form a bubble here because it's kind of easiest to visualize. All right, and so this little bubble here, okay, has gas water in it, right? Vapor, right? And this vapor has vapor pressure, so it's pushing against the outsides of your bubbles here. Okay, and it's got some pressure in here. Now, remember that you also have pressure, your atmospheric pressure up here. So this is your vapor pressure. Okay, and then you also have your atmospheric pressure up here. All right, and so the atmospheric pressure is pushing down on the surface of your liquid at 14.7 psi or 1 atmosphere, however you want to measure it. Okay, so this pressure from the atmosphere is pushing down, and if this vapor pressure is weaker than the atmospheric pressure, then this bubble will get squashed. Okay, that makes sense. Like if you take, a piece of, if you take a ball out of some rubber ball or some like a Kinder egg or some chocolate egg, right? And you start piling books on it, that egg is going to be able to support those books until it's holding too many books and then it gets squashed. Same thing with the bubble. If your bubble doesn't have enough vapor pressure pushing up against the atmosphere, then it'll get squashed by the atmosphere. Okay, and so once these two are equal to one another, then this bubble can survive. All right, so that's essentially what needs to happen is this vapor pressure bubble has to equal the atmospheric pressure. If these two things are not equal to one another, then the bubble gets squashed. But then once the vapor pressure is equal to the atmospheric pressure, all right, once the vapor pressure is equal to the atmospheric pressure, your bubble can survive, and we all know that once that happens, these bubbles start rising to the top and you start boiling. So the key to boiling is that it can happen throughout the solution. Okay, we see it at the bottom, all right, when we're boiling water solution. Okay, when we're boiling water, because that's where the heat starts. But if you let the water get hot enough, you'll actually see bubbles form throughout the whole thing. All right, and then the other thing, this is the real definition, is that the vapor pressure, okay, the vapor pressure has to equal the atmospheric pressure. All right. So that's essentially what we get to. Now the next couple of slides just kind of talk about what we just talked about. So the boiling point is defined as the temperature at which the vapor pressure of liquid equals the external pressure. So the vapor pressure of the liquid equals the external pressure. That's important. That's the definition of boiling. All right, and specifically the boiling point is the temperature where that occurs. There's two ways that you can make something boil. You can raise the vapor pressure, and remember when we talked about vapor pressure in a previous video, we talked about how one way to increase the vapor pressure is by increasing the temperature. Increasing the temperature gives all of them more kinetic energy. It's going to shift that graph to the right, so more of them are past that dashed line. All right, so once more of them are past that dashed line, then more of them will be able to escape into the vapor, thereby increasing the vapor pressure. All right, and that's what you do in your kitchen at home when you're making noodles, is that you're increasing your vapor pressure by by increasing the heat of the water by putting it on the stove. All right. The other way we can make things boil is by lowering the external pressure. So if we lower the external pressure enough, that means it's not pushing down as hard on top of that solution. And so the vapor pressure does not have to be as high in order to get it to boil. Okay, but essentially what this means is your liquid particles have to have enough kinetic energy to break the intermolecular forces and then overcome the force of the external pressure. All right. So steps to get to the boiling. All right, heat is added or pressure is decreased or both. You know, at the boiling point, the temperature remains the same even as you had heat. All right, and we'll see this clearly. Okay, here in a second when we look at heating curves. The additional heat used to increase the kinetic energies break the intermolecular forces, and then after all has boiled, once all converted to a gas, the temperature will increase if heat is still being added. So here's our heating curve. This is for water. So starting down here in the bottom left, or sorry, the y-axis here is temperature in Celsius, and then we're adding heat as we're going to the right this way. All right, so down here we have we just have ice, and it's at negative 30 degrees Celsius. All right, pretty cold. All right, and then we're starting to add heat. Notice that as we add heat, our substance is starting to raise temperature until we reach this point here where we begin melting. Right, so this is where we start melting. In between these 2 points right here, okay, we have ice and water together. Now notice that as we heat, we started here, at this point we only had ice. We started adding heat to this. Heat comes in and it starts melting the ice. Notice that the temperature does not change while that ice is melting. All right, until we get to this point here where we only have water left. There's just water right here. Okay, and then now that all the ice is melted, our temperature can start increasing again, and the water starts getting heated up, heated up, heated up, heated up, heated up, heated up, until we get the boiling point at 100 degrees Celsius. And then the same idea, we only have liquid water here. Okay, so maybe I'll label this as water right here. So this is water, and then from here we have water and steam. Okay. We have a mixture of both of them, water and steam here. And then so this increases temperature, or this adds heat, and so the water is starting to vaporize, essentially boil, right? And then now that we're at this point, we only have steam left, and then we can increase heat from there. So that's a heating curve. All right, and you should be able to read this, and for any substance, really. But a couple of important things is notice that anytime we have a phase change, our temperature cannot increase. That's important. All right. So boiling point depends on the pressure. So the higher the air pressure, the higher the boiling point. All right. The lower the air pressure, the lower the boiling point. All right. And we just kind of talked about this, about the fact that if you lower that atmospheric pressure, that outside external pressure, then your vapor pressure doesn't have to get as high. So you don't have to get as high of a temperature. Okay, and so we don't need to be as high if our vapor pressure is lower. Vice versa, if our boiling point, or if our vapor pressure is, or if our external pressure is higher, then we have to get to a much higher temperature. So there's a couple of applications for this. If you're, you go to the mountains and you're trying to cook macaroni and cheese, it'll actually take you longer to cook your macaroni and cheese than it would at wherever you're living now if you're at the top of a mountain. And that's because at a higher altitude, you're at a lower external pressure. So your vapor pressure doesn't have to be as high, so it's going to start boiling at a lower temperature. Okay, so it won't be super drastic unless you're really high up. Right, but it'll start boiling at 98 or 97 instead of 100 degrees Celsius. And because it's boiling at a lower temperature, the water has less heat to give to the noodles. Noodles don't cook because they're in boiling water. They're cooking because they have the heat from the liquid, from the water that they're cooking in. All right, and if you're at a lower temperature, then you have less heat to go around and your noodles cook slower. And vice versa, you've probably heard of Instapots or pressure cookers. Essentially all those do is you cap your whatever you're baking your thing in or cooking your thing in, and then it increases that external pressure, so the water will start boiling at a much higher temperature, and because it's at a higher temperature, then you'll have generally more energy in there to cook whatever it is you're trying to cook. All right, last little bit here, because now that you understand that our boiling point doesn't just happen at 100 degrees Celsius, it happens at a range depending on what the external pressure is, we have to define a normal, okay? And the normal is the thing that we're just always going to refer to. And so the normal boiling point is the boiling point of a liquid at standard pressure. So this is assuming that you're not changing the pressure and you're right at 1 atmosphere. This is standard pressure. All right, so the normal boiling point of water is 100 degrees Celsius. And everything has a different normal boiling point, but that's essentially all it is. All right, and that's it for this video. Let me know if you have any questions, and I'll see you on the flip side.